All right, let's look at a simple example here. Example, find the solution of following IVP. The following IVP initial value problem. Let's say y double prime plus 4y equals 0 with y of 0 equals y prime of 0 equals 1. So the very first thing we can do to solve a differential equation, higher order ODE, is to find the characteristic equation. Once we know the characteristic equation and once we know the roots of the characteristic equation, we can also find the solutions of the linearly independent solutions of our ODE, and then we can find the general solution, and then we can find the constants using the initial values. So here the characteristic equation is so for the characteristic equation, I have to use the same coefficients, but instead of derivatives, I have to use power. So instead of second derivative, I'll use second power 2. So r to power 2 plus 4 equals 0. Here the roots are r equals plus minus root minus 4, because r squared will be minus 4 and r will be plus minus root minus 4. And this one I can write it as plus minus root minus 1 times root 4. Root 4 is 2, so I can write it as plus minus 2i. Root minus 1 is I, and root 4 is 2, so I can write this one as plus minus 2i. And so these are the roots for our characteristic equation. So the two linearly independent solutions will be the linearly independent solutions What were the linearly independent solutions? E to power alpha x cos beta x and e to power alpha x sine beta x. Here alpha is 0. Remember, if we were assuming that our roots are alpha plus minus I beta. Here the roots are plus minus 2i. So there is no alpha. Alpha is 0. And the solutions should be e to power alpha x cos beta x and e to power alpha x sine beta x, but alpha is 0. So I don't have any e to power alpha x term. E to power alpha x term will be e to power 0, which is 1. So I'll be left with cos beta x and sine beta x. So y1 equals e to power alpha x cos beta x. Here alpha is 0, beta is 2. So this is cos 2x. And y2 equals e to power alpha x sine beta x. Again, alpha is 0, beta is 2. So this is sine 2x. So these are two linearly independent solutions, and therefore the general solution will be y double prime plus y equals 0 will be y double prime plus 4y equals 0 will be y equals c1 y1 plus c2 y2. So that's c1 cos 2x plus c2 sine 2x. C1 cos 2x plus C2 sine 2x And to find C1 and C2, use the initial conditions. Initial conditions here are y of 0 equals y prime of 0 equals 1. These were my initial conditions. So y of 0 equals 1. That gives me C1 equals 1, because y of 0 will be C1. What about y prime of 0? Y prime derivative of this function at 0. Derivative of this function will be minus 2c1 sine 2x at 0, that's 0, plus 2c2 cos 2x at 0 will be 2c2. So 2c2 will be also 1. That gives me c2 equals 1/2. So y will be equal to c1 is 1. So cos 2x plus 1/2 sine 2x. This is the solution of IVP y double prime plus 4y equals 0, with y of 0 equals y prime of 0 equals 1. All right, now let's look at higher order ODEs. Here we looked at second order ODEs and the homogeneous one, because we still, all of the equations that we considered right hand side was 0. So we're still doing homogeneous equations, but homogeneous second order. Now let's do homogeneous higher order, like third order or fourth order. So now we will try to solve higher order linear, higher order homogeneous ODEs. Or let's do let me say higher order ODEs for now, and as a special case, then I'll consider homogeneous ones, higher order ODEs. So let's look at the existence and uniqueness first. Existence and uniqueness of the solution. So let's consider the equation of the form, let's say y nth derivative. So first we want to know when the solution exists and is unique, and then we want to try to find it. First, we have to have a guarantee for existence and uniqueness of the solution, and then we'll try to find the solution. So let's consider y nth derivative plus p n minus 1 of x, y n minus 1 derivative, all the way to p1 of x, y first derivative, plus p0 of x times y equals f of x, where Pn minus 1 of x all the way to P0 of x and f of x are continuous functions. So again, we need the assumption of continuity for our coefficients in order to guarantee existence and uniqueness of the solution. This happened in the second order as well. As long as the coefficients are continuous functions, then we can guarantee existence and uniqueness. In the special case, if the coefficients are constants, so constant coefficients, of course, constant functions are always continuous. So we don't have any concern in that case. But in general, if the coefficients are continuous functions, then we can guarantee existence and uniqueness of the solutions. So consider this where these are continuous functions, then this ODE, then the ODE above, then the ODE above with the initial conditions, let's say y of A equals B0, y prime of A equals B1, all the way to y n minus 1 derivative at A equals, let's say, B n minus 1, has a unique solution. So here A is any number in the domain. So I'm assuming that all functions are continuous in their domain. So if they're continuous on all real numbers from -infinity to infinity, then A could be any number. But if they have a particular domain, if they're continuous on a particular domain, then A here, this number A here, has to be in the domain of those functions where they are continuous. But let's assume for now, for simplicity, that all these functions are continuous everywhere from -infinity to infinity, and then this A could be any real number. So as long as you have a differential equation of this form with n initial conditions, because this differential equation is of order n, so we need n initial conditions. So if you are like, this is 1, 2, and all the way to this is the nth initial condition. So if you have n order differential equation with n initial conditions and all the coefficients and also the function on the right hand side are continuous, then we can say that the solution exists and is unique. So now that we know under this condition the solution exists and is unique, then the question is, how can we find the solution? Or how can we find the general solution? So how to find the solution? So let's consider the homogeneous equation for now. Let's consider the homogeneous nth order ODE of the form y nth derivative plus p n minus 1 of x, y n minus 1 derivative, all the way to p1 of x, y prime plus p0 of x times y equals 0. We will consider non-homogeneous equations and how to solve it later after this topic. But still, let's for the moment, let's consider on the homogeneous equation where the right-hand side is 0. And we want to find the general solution of this equation. So let's ignore the initial conditions for now. If I can find a general solution, then it will be very easy to find the constants like C1 to Cn using the initial conditions. So finding the constants using the initial conditions is very easy. So for now, let's focus on finding the general solution of this equation without any initial conditions. So in order to find the general solution, of this ODE, first we need to find n linearly independent solutions y1 to yn, and then the general solution can be written as y equals c1y1 plus c2y2 all the way to cnyn. And here c1 to cn are constants. So the recipe is very simple and similar to second order ODE. In second order ODE, we needed two linearly independent solutions, y1 and y2, and the general solution was c1y1 plus c2y2. Here we have nth order differential equation, so we need n linearly independent solutions, y1 to yn, and then the general solution will be c1y1 plus c2y2 all the way to cnyn. And now the only question is, how can we find these y1 to yn, like the linearly independent solutions y1 to yn? So how to find the linearly independent solutions y1 to yn? So again, still the recipe is similar to what we did for second order ODE. How did you find y1 and y2 in the case of second order ODE? First, we had to find the characteristic equation. Then we found the roots of the characteristic equation, and we used that to find the linearly independent solution. So we have to do the same thing here. So similar to second order ODEs, first we need to find the characteristic equation of the given ODE. Then find its roots, find the roots of it, find its roots. Say y1, say r1 to rn. And then use these roots to find y1 to yn, noting that so there are a few things that we have to note here. So first of all, if let's say Ri is a simple root, simple real root, with multiplicity 1, then we consider e to power Rix as a solution. So multiplicity of a root, it's the number of times that the root is repeated. So if you have a simple root where it's not a repeated root and therefore multiplicity 1. So in general, let's say if you have x minus a to power, for example, n appeared in your polynomial, then we say that a is the root of that polynomial with multiplicity n. So this number here is called multiplicity. So if you have a repeated root, for example, x minus a to power 2, then it's called multiplicity 2. But multiplicity 1 means just not, it means not a repeated root. For example, x minus a times x minus b, then these are simple roots or roots with multiplicity 1. So if you have a multiplicity 1 root, real root, then we have to consider e to power rix. So for example, if 5 is a root of, when I say root, I mean root of the characteristic equation. So for example, if 5 is a root of the characteristic equation, then we have to consider e to power 5x as one of the solutions. So that's one thing. What about if you have complex roots? So second thing that we have to note is that if, let's say, alpha plus I beta and alpha minus I beta are simple complex roots, with multiplicity 1, of our characteristic equation, or for our characteristic then what will be the solutions? Then we can consider e to power alpha x cos beta x and e to power alpha x sine beta x. Will be solutions. So the recipe in the case of simple roots is simple. You know, just if it's real root, e to power rx, complex roots, alpha plus or minus I beta, e to power alpha x cos beta x, e to power alpha x sine beta x. And what about if we have repeated roots? Roots with multiplicity more than 1. For example, if 5 and 5 and 5 are roots. So if Ri is a real root with multiplicity ni, let's say if Ri is repeated ni times, then what will be the corresponding solutions? So for example, we saw if a root is repeated twice, let's say for example 2 and 2 are the solutions, then e to power 2x and x times e to power 2x were the solutions. Now here, if for example 2 is repeated 3 times, let's say 2 and 2 and 2 are the solutions for the characteristic equation, then what will be the solutions for ODE? E to power 2x, x e to power 2x, and the next one will be x squared e to power 2x. So we just need to raise power of x by 1 unit each time. So if Ri is a real root with multiplicity ni, then e to power rix, x e to power rix, x squared e to power rix, all the way to x to power n minus 1 e to power rix will be the solutions of our ODE. And finally, if we have complex roots, which are repeated roots as well, with multiplicity more than one. So if, let's say, alpha plus I beta and alpha minus I beta are roots of the characteristic equation, with multiplicity again ni, let's say, then what will be the corresponding solutions? So for alpha plus I beta and alpha minus I beta, if multiplicity was 1, then we had to consider, as we said, e to power alpha x cos beta x, e to power alpha x sin beta x. Now, if they are, let's say, multiplicity 2, in addition to these two solutions, I have to consider x times this solution and x times this solution. Similarly, if there are, let's say, multiplicity 3, in addition to these solutions and x times this and x times this, I have to also consider x squared times this and x squared times this. So similarly, for multiplicity ni, I have to consider, this was ni minus 1. I have to consider the solutions as e to power alpha x cos beta x, e to power alpha x sin beta x, x e to power alpha x, x e to power alpha x cos beta x, x e to power alpha x sin beta x, all the way to x to power ni minus 1, e to power alpha x cos beta x, and x to power ni minus 1, e to power alpha x sin beta x. So these will be the solutions. These will be the solutions that we have to consider, the linearly independent solutions that we have to consider corresponding to these roots of the characteristic equations. So we covered all possibilities here. So either you have simple real roots or simple complex roots, or repeated real roots or repeated complex roots. So we considered all possibilities here. So now let's look at some examples to see how we can apply these methods. So to find y1 to yn. So here you use these 4 cases to find y1 to yn. Once you have your y1 to yn, then the general solution can be written as c1 y1 to cn yn. So let's look at some examples now. Example, find the solution of this following ODE. Let's say find the general solution of y third derivative minus 3y double derivative minus y prime plus 3y equals 0. So this is part A. Part B, find the solution. Find the solution of the ODE above. With the initial conditions. With the initial conditions, y of 0 equals y prime of 0 equals 1, and y double prime of 0 equals 3. So here we have a third order ODE. So if we wanted to have a unique solution, then we need 3 initial conditions. So in part A, no initial condition was given, so we can find the general solution in terms of some constants, C1, C2, C3. And in part B, we can find those constants C1, C2, C3 using these 3 initial conditions. So in part A, where we want to find the general solution of this ODE, first we need to find the characteristic equation. Once we have the characteristic equation of this ODE, we can find the roots of the characteristic equation, and then we can go from there. So part A, first find the characteristic equation. Characteristic equation of ODE above. Characteristic equation, I have to use the same coefficients. Instead of derivatives, I need to use powers. So it starts with r to power 3 because we start with y third derivative. So the characteristic equation starts with r to power 3 minus 3r squared minus r prime and minus r plus 3 equals 0. Minus y prime, that y prime will be replaced with r to power 1 because it's y first derivative. So in characteristic equation will be replaced with r to power 1, and then it's plus 3y. Y means 0th derivative, so it will be plus 3r to power 0, and r to power 0 means 1, so it means plus 3 equals 0. Next, we need the roots of this characteristic equation. Next, we need to find the roots of this equation. So this is a cubic equation. If we want to find the roots, we can try to guess one of the roots. If we can guess one of the roots and we find the root, one root that way, then we can divide this polynomial by r minus that root using the long division algorithm. And then we will find the other factor, and then we can find the other roots as well. So this is how we solve cubic equation you learn in pre-calculus. So let's first try to guess one root. And we know that if there is again, from pre-calculus, hopefully you have seen that if this has a integer valued root, then that has to be a divisor of this number here, as long as this number is 1. So we can try plus or minus 1 here, or plus or minus 3 divisors of this number. Well, if we replace r with 1, 1 minus 3 is minus 2, minus 1 is minus 3, plus 3 is 0. So r equals 1 is a root of this equation. So r equals 1. We say guess one root. R equals 1, then we'll have 1 minus 3 plus 1 minus 3 minus 1 plus 3. So r equals 1 is a root. That means r minus 1 is a factor for r cubed minus 3r squared minus r plus 3. If r equals 1 is a root, then r minus 1 is a factor. So this is also a something you learn in pre-calculus, that if r equals a is a root, then r minus a is a factor for your polynomial. So here r equals 1 is a root, r minus 1 therefore is a factor. So to find the other factor, use the long division. Or we can just simply write r cubed minus 3r squared minus r plus 3 equals r minus 1. We know it's one factor. The other factor should start with r squared, because see, this guy times this guy should give me r cubed. So r squared times r gives me r cubed. So it starts with r squared. And then it has to end in minus 3. Because minus 3 times minus 1 will give me plus 3. Right? So this constant times this constant must give me plus 3. So this is minus 1. This should be minus 3. And what coefficient should I write for r? So if I write, for example, plus r, this gives me r squared minus, see, I will have minus 1r squared here, but I need minus 3r squared. So this should be how many r? This should be minus 2r. Because then minus 2r times r will give me minus 2r squared minus 1 times r squared. Overall will be minus 3r squared. And the other coefficient must be automatically generated. So here, see, minus 1 times 2r minus 2r is plus 2r, minus 3r is minus r, which is what I have here. So the first coefficient and last coefficient was very simple, because the first coefficient I need to, I knew that I have to write it in a way that this times r must give me r cubed. That has to be r squared. The constant is very easy to find out, because this constant times minus 1 must give me plus 3. So this has to be minus 3. And this coefficient here times, I have to choose it in a way that I'll get minus 3r squared here. So I already have minus r squared here. So this should be minus 2r squared, so that I'll get minus 3r squared in total. So that's why I wrote minus 2r here, times r will give me minus 2r squared, minus r squared will be minus 3r squared. And to verify your answer, you can check the coefficient of r, which has to be minus r. So it is minus r here, because minus 1 times minus 2r is 2r, minus 3r will give me minus r. So this is the factorization of this cubic polynomial. So to find the other two roots, I need to find, so I already know that r equals 1 is one root. To find the other two roots, I need to find the roots of this equation. So the roots of the characteristic equation are r equals 1 and r equals the roots of this minus b2 plus minus root 4 minus 4a, so plus 12 divided by 2. So this is 2 plus minus root 16, which is 4 divided by 2. So this is 2 plus 4, 6 over 2, 3. And 2 minus 4 minus 2 over 2 minus 1. So we found three roots. R1 equals 1, R2 equals 3, R3 equals minus 1. So all of these, basically we are in case 1 above, because they are all real valued roots and they're all simple. They are not repeated. I didn't find 3 twice. If, for example, I find 3 twice here, let's say if I get, for example, 2 plus minus 0 over 2. Then it will be 1 and 1, and that would be a repeated root. But here there is no repeated root. Each of these roots occurred only once. So 1 occurred once, 3 occurred once, minus 1 occurred once. So 3 simple roots, 1, 3, and minus 1. 1, 3, and minus 1, which we already covered the recipe and the algorithm in case 1. Let's say case, I wrote 1, this type of 1. Case 1 above. So in case 1, we said that if you have real valued roots, simple real valued roots, Ri, just consider e to power Rix as your solution. So our linearly independent solutions will be, so by 1 above, the linearly independent solutions for our ODE will be y1 equals e to power R1x, is e to power x, y2 equals e to power R2x, which is e to power 3x, e to power 3x, and y3 equals e to power R3x equals e to power minus x. And then the general solution will be y equals c1 y1 plus c2 y2 plus c3 y3. That's going to be c1 e to power x plus c2 e to power 3x plus c3 e to power minus x. This is the general solution. We found y1, y2, y3, 3 linearly independent solutions. And then the general solution with c1, y1 plus c2, y2 plus c3, y3. So that's the solution for part A. We found the general solution for our ODE. And in part B, if you want to find c1, c2, c3, so let me leave part B as exercise. It's very simple. Part B, if you remember, the initial conditions were given and you wanted to find the solution. Well, we already know the general solution, the form of the general solution. And if you have the initial conditions, 3 initial conditions, you will have 3 equations with 3 unknowns. Here you have 3 unknowns, C1, C2, C3. And you have 3 initial conditions, or if you write them down, you'll see that you will have 3 equations with 3 unknowns, C1, C2, C3, and you can find, solve that system with 3 equations, 3 unknowns to find your C1, C2, C3, and then you will have your solution. Okay, the next example. Suppose that the characteristic equation of an ODE is, let's say, r squared plus 1 the whole square times r minus 3 equals 0. Find the general solution of this ODE and also find the ODE with the above characteristic equation. and the ODE with the above characteristic equation. So the characteristic equation is given. So it's opposite situation of what we had in the previous example. In the previous example, ODE was given. And in order to solve it, we had to find the characteristic equation. Here, the characteristic equation is given. So one step is already done for us. And we want to find the general solution. And we also want to know which ODE has this characteristic equation. So far, we had the ODEs and we found the characteristic equations. This time it's the opposite. We have the characteristic equation. We want to know which ODE has this characteristic equation. So first, let's find the general solution of the ODE. So here the characteristic equation is of which degree? Because see, this is degree 4 times degree 1. Overall is degree 5. So characteristic equation is degree 5, which means the ODE is of fifth order. So here, answer here, the characteristic equation has degree 5. So we have a fifth order ODE. So the general solution will be y equals C1y1 plus C2y2 plus C3y3, C4y4, and C5y5, where y1 to y5 are linearly independent solutions of our ODE. So we just need to find y1 to y5, and then the general solution is C1 y1 all the way to C5 y5. And how can you find y1 to y5? We need to find r1 to r5, the roots of the characteristic equation. So to find y1 to y5, find the roots of the characteristic equation. Roots of the characteristic equation. So the characteristic equation is r squared plus 1 squared times r minus 3 equals 0. So here, of course, one solution r1 equals 3. And r squared plus 1 equals 0. That gives me r squared equals minus 1. That gives me r equals plus minus root minus 1 equals plus minus I. But each of these roots have multiplicity 2 because of this power here. See, I have a power here, which means that I have a multiplicity 2 for each of the roots of this factor. This factor has 2 roots, r equals I or root minus 1 and r equals minus I or minus root minus 1. Each of them have multiplicity 2. So here, basically, the roots are each with multiplicity 2. So we can say that the roots are r1 equals 3, r2 equals r3 equals I, r4 equals r5 equals minus I. And then we need to find the solution corresponding to each of these roots. So the corresponding solutions are y1 equals e to power r1x, which is e to power 3x. And this is what we said, what we covered in case 1. In case 1, we said if you have a simple real root ri, then we just need to simply consider e to power rix as a corresponding solution. And we also said, like, if you have a plus minus alpha plus minus I beta with multiplicity more than 1, that's what we covered in case 4. Look at case 4. Case 4, we said if you have alpha plus I beta and alpha minus I beta, here we have 0 plus I and 0 minus I, or I and minus I, with multiplicity 2, because I and minus I, each of them occurred with multiplicity 2. Then the corresponding solutions are e to power alpha x cos beta x, e to power alpha x sine beta x e to power alpha x cos beta x e to power alpha x sine beta x. And these will be the solution, because ni here is 2, so ni minus 1 will be 1. So I just need to consider power of x all the way to ni minus 1, which means all the way to 1. So I will have 4 solutions here. Alpha is 0, beta is 1. So cos beta x, sine beta x cos beta x, and x sine beta x. So 4 solutions. Also, y2 equals cos beta x, which is cos x. y3 equals sine x, y4 equals x cos x, y5 equals x sine x. So these are the basically according to the recipe or the algorithm that we explained in case 4 above. E to power alpha x cos beta x, e to power alpha x sine beta x e to power alpha x cos beta x, and x e to power alpha x sine beta x. And then the general solution, as we said, once we have the linearly independent solutions, we can write the general solution as y equals c1 y1, c1 e to power 3x, c2 cos x, c3 sine x, c4 x cos x, c5 x sine x. This will be the general solution of our ODE. And the other part, finding the ODE itself, finding the ODE. So we know that there is a close connection between the ODE and the characteristic equation. They have the same coefficients. The only difference is that instead of powers of R, I need to have derivatives in my ODE. So we will expand the characteristic equation and we will use the coefficients to find the ODE. So what is the characteristic equation? Characteristic equation is r squared plus 1 to power 2 times r minus 3. So I can easily expand this just using high school algebra. Then I will have r to power 4 plus 2r squared plus 1 times r minus 3. And then this one I can write it as r to power 5 minus plus 2r cubed plus r minus 3r to power 4 minus 6r squared minus 3. This one I can write r to power 5 minus 3r to power 4 plus 2r to power 3 plus r minus 3. So the corresponding ODE will be y fifth derivative. I have to use the same coefficients. The only difference is that instead of powers for r, I will use the derivatives for y. So r to power 5 will be replaced with y fifth derivative minus 3y fourth derivative plus 2y third derivative plus y first derivative, which means y prime, minus 3y, because this is r to power 0, and that will be replaced with y to power y zeroth derivative, which is y itself. 3y to zeroth derivative, which is y, and then this will be equal to 0. R to power 5 replaced with y fifth derivative, r to power 4 replaced with y fourth derivative, r to power 1 replaced with y first derivative. 3, this is minus, and I use the same coefficients, 1 minus 3, 2, 1, 1 minus 3, 2, 1. And minus 3 means minus 3 times r to power 0. The corresponding term will be minus 3 times y zeroth derivative, which is y, and then equals 0. This will be the corresponding ODE. The corresponding ODE for this characteristic equation, which has this general solution. So unlike the previous example where we started with the ODE and we found the general solution, this time we started with the characteristic equation. We used the characteristic equation to find the general solution. Once we had the characteristic equation here, we had the characteristic equation. We found the general solution because once we had the characteristic equation, we could find the roots. We used the roots to find y1 to y5. And then we found the general solution as C1, Y1, all the way to C plus to C5, Y5. And we could also find the original ODE. We could find out which ODE has this characteristic equation. How? Because we know that there is a very close connection between characteristic equation and the ODEs. They have the same coefficients. The only difference is that powers of r will be replaced with derivatives of y. Okay, guys, so that's all for today. And we learned how to solve homogeneous higher order ODEs. So thank you and see you next time.